All right, we have established a lactic acid and sodium lactates mixture, and we've done a problem where we add the strong acid to it, and we determined that the pH was not changed dramatically by adding that strong acid. Now we're going to take that same sodium lactic acid mixture, and we are going to add a strong base to it. And so we have the same reaction as we had in the previous problem, where we have that lactic acid, weak acid problem. And that's going to be a weak acid reaction, C3H5O3 minus. We also are going to have our sodium lactate reaction that's going to break up 100% because it's a salt. And we have Na plus with this lactate ion. And now, because we are adding a strong base, we have this NaOH is going to break into Na plus and OH minus. And in order to do this, we are going to have to first find out how many moles of each of our species we have. We aren't changing the amount of lactic acid or sodium lactate, so we know that the number of moles of each of those we've already determined are 0.012 moles of that and 0.01 moles of this. And we know that this is going to break up 100%, so this is also going to be 0.01 moles. Now we are going to be adding 10 milliliters of 0.1 molar NaOH. So to find the number of moles, I have 0.1 molar. How many moles in 10 mils, or 0.01 liters, by moving the decimal over 3 spots, and I will get 0.001 moles of NaOH, and therefore OH minus. Okay, so now we have the number of moles of each species. The next step, or the next slide, is set up our equilibrium expression. And so I'm going to go to the next slide here, maybe. And the equilibrium we have set up. Now remember, we have to think about both of the 100% reactions. So that happens and gives us 0.001 moles of this, and our sodium lactate problem forming Na plus and C3H5O3 minus. But now when we add this strong base to it, our equilibrium expression is going to look the same, except that hydroxide, a strong base, really wants to go out and find a hydrogen. So it's going to react with our lactic acid, and it's going to be a reaction 100% to form these products because it really wants that hydrogen. It's going to pull that hydrogen right off. And so we have an ice table, but it's not really an ice table. This would be more of like an end point, not an equilibrium point. We started with 0.012 moles of this, 0.001 moles of this, and 0.01 moles of that. Water is a liquid, so we don't have to worry about that. Now, because this is going to search out and try to get those hydrogens off, that is going to be our limiting reactant. And so 0.001 of this will be removed, 0.001 of that removed, and we're going to add 0.001 of that lactate ion, leaving us with 0.0110, Fix that up a little. Okay. Now, you'll see that I have this lactic acid and lactate ions in solution, and just like the previous problem, that those two ions in solution are going to try to find their equilibrium point, where enough lactic acid breaks up to form H plus and the lactate ion. And so now this is a true equilibrium ice table with this ending at equilibrium, but now my initial concentrations are what I ended up with after that strong base reaction. I have none of this and 0.011 of this. Because I have no hydrogen, I'm going to have a reaction that goes right, adding X here, and I will end up with 0.011 minus X, X, and 0.011 plus X. And so when I write a Ka expression, it's products or reactants, so X times 0.011 plus X over 0.011 minus X. And just like all of our other previous problems, we're going to say that X is much, much smaller than 0.011, and the Ka was 1.4 times 10 to the negative fourth. And actually this one becomes easy because my 0.011 reduces out, and so X is equal to 1.4 times 10 to the negative fourth. When we divide by 0.011, it is less than 5%, and so that X is negligible. I can solve for the pH. One sidebar kind of comment here, that these are all in moles. When I divide it by 0.11, because I had 110 mils, divide by 0.11, this is going to be divided by 0.11, and this is going to be divided by 0.11, which also cancels out. And so this is already a molarity for me, and so when I take negative log 1.4 times 10 to the negative fourth, I will get a pH of 3.85. And you'll notice that this also is not a significant change in pH considering we added a strong base. The reason for that is because we have that common ion, that lactate ion, that helps take some of that buffering capacity. The lactate ion along with the lactic acid, having both of them present, allows the pH not to change significantly. We are going to be talking about buffers next.